Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, we got the power! Woo-hoo, power! Today we're going to talk about power. Oh, power, power, power. Power's a weird thing, but it's awesome. Power is a measured thing. It's this. Work. Work with me, work with me. Work done. Work done in a period of time. So now we have work and time factored. So here's the, maybe it's easy to say this. The faster that work is done, the more the power. If you understand that, I think you're gonna get the idea. This is the equation for power. Power's P, makes sense, right? Power is work divided by time. Now let's think about this. Think about this. Work is force times distance, so it's FD over T. And if we wanted to do the math and the unit things, force is a Newton, but that's MA, so that's going to be a kilogram, meter per second squared, times a meter, that's the distance, all divided by time, which is in seconds. So one of the seconds cancels, so it's kilogram meter squared over a second. And that, we give a new name. We call it a watt. You've probably heard about kilowatts, such like that, and or simply a W. All right. Or you might also think of it, because if you break this down, work is a, don't get the watt confused with work, by the way. This is the unit and this is the dimension. That would be a joule per second. All right, so that's what power is. And also, let's take another thing. So 1 watt is a simple measurement, okay? But there's also another term we often hear. You've heard this when we talk about power. You might have heard of horsepower. And it turns out there are 746 watts is equal to 1 horsepower. When they were inventing the idea of horsepower, they were trying to say, what is the power of 1 horse? Okay? Turns out that they were very liberal. Turns out that a horse can't produce, the average horse, can't produce 1 horsepower of work. They can only produce about 2/3 of a horsepower, as it turns out. So that's kind of weird. But that's how it was determined. Someone was very generous when they were figuring out power back in the day. Okay? How much power can you produce? Well, if you're an elite athlete, then you can probably produce 300 watts, okay? Which is about a half of a horsepower. So 300 watts for elite athletes to do it over a period of time. And many of you know that I do triathlons. And when I do triathlons, actually, I wear a power meter. My actually watch right here I'm wearing measures power. There's a device on side of my bicycle that measures what my power output is. And I occasionally measure, it's actually probably higher than 300. Maybe it's 400 for really elite athletes. Because I would measure what we call my functional threshold power, which is the amount of power I could produce for an hour, like with a gun held to my head. Like I'm working everything I can have. And I would measure this amount. And I was like in, last time I did a big race, I was like about 240 watts. That's how much I could hold for 1 hour. And then I'd be done, completely spent. When I big long triathlon races where I like ride my bike 112 miles, crazy stuff like that, I would actually try and ride my bike at 160 watts because that's a lot less, and that's something I could maintain for 6 hours as opposed to 1 hour. And there's a bunch of math on this, but watts really make a big difference. It helps us to understand things. Maybe another place that you've seen this that's kind of important. You ever heard on a commercial this?
Hi, I'm Kate on 0 to 60 with your auto news. Speeding up to first place is Nissan's GTR Nismo with a new drifting record of 189.49 miles per hour.
You can go from 0 to 60 in so many seconds. So when we think about a car, you know, it's the ability to accelerate. That's what we talk about for power. That's another way to look at power. And if you think about it like mathematically, if power is work divided by time, right, I could actually just rearrange that. I could say time is power divided by work. And so the smaller that number, the more power I have. And so that's because I can go from, 0 to 60 miles per hour, in 1.2 seconds, then that's going to have a lot of power for me to get that going. So it's basically how fast can I go fast? Write that down. That's pretty cool. How fast? All right, and you've probably seen engines that says it's got so much horsepower, and if it's got a bigger horsepower, it's got a bigger engine, et cetera, et cetera. One last thing about this that I think is fascinating, we'll go back to bicycling. When I measure myself, I can measure these numbers, but it turns out, probably not surprising to you, but if there are bigger people, I'm not a very big person, big people can put out more watts, but that doesn't make them faster. Because if they're big, they have more mass to overcome. Right? Because when you measure speed, what you really want is the number of watts per kilogram. The higher this number is, the faster you'll go. So let's say you have a very small individual, maybe a 120-pound person or 100 and whatever, and they put out the same watts as I do. I don't weigh 120 pounds. I weigh more than that. They are going to go faster than I will because they are moving less mass, and so that's going to translate into a faster bike portion of a triathlon. So we look at the watts per kilogram. So I do these races online, and in these races online, if I'm racing somebody with the same exact watts, but they're lighter than me, they win every time. It's actually like a cycling race. I know these exist, where you're racing online against other people, and my bicycle I have to do all the work myself. Let's do a few examples. Example 1, we've got a car, and the car wants to pass the truck. All right, the mass of the car is, so here's the deal. He wants to pass this truck on the road. He's got an initial speed of 13.4 meters per second. To pass it, he needs to pass it at 17.9 meters per second in 3 seconds. So what kind of a power does he need to have to pass the truck? Okay, so if power is work over time, there's my time right there, so I need to find the work, all right? And we've got initial and final velocity, so we're going to use our kinetic energy equation, right? This one right here, so I know my half. You plug this all in, all right, and you come up with 91,600 joules. We plug this into here, and we come up with 30,533 watts. Now that might be kind of a weird number. We then, if we want to, we could divide that by 746, that's horsepowers, and you need a 40.9 horsepower engine to solve that. So if you don't have a 40 horsepower engine, game over. You shouldn't be passing. You got one of those, gutless wonders cars, right? Let's rearrange some stuff. I think this is a fascinating thing, right? So we know that work is force times distance, and we know power is work divided by time. All right, so if we plug in FD into W, we can say FD over T. But if you think about it, what's D over T? That's the velocity. So you can say P is equal to F times the velocity. Make sense? So this is another equation. Jot this down. An important equation to know that power is the force times the velocity. Let's take a look at an example here. Let's say that we have a car traveling up a 5-degree incline. All right? And it takes a force of 1,280 newtons to keep it moving. The mass of the car is 1,500 kilograms. And if the engine delivers, so the power is 50 horsepower, so it's a 50 horsepower engine, what's the maximum speed? This is a good question. How fast can this car travel up this 5-degree import, given the fact that it has a 50 horsepower engine? Now the first step we need to do, all right, is I'm going to convert this to watts, because all of our numbers have to be in watts and seconds and kilograms and seconds. So let's go ahead and do that right away. Basically I take this, and as we know, there is 1 horsepower is equal to 746 watts, and that comes out to 37,300 watts. So we need to know that. But we can use our cool equation over here. What's the equation? P is equal to FV. What's P? 37,300 equals the force. The car consistently produces a 1280 Newton force times V. Divide both sides by V, or by 1280 to get V, and you get 29 meters per second. By the way, if you convert that to miles per hour, that's about 65 miles per hour. So this car with a 50 horsepower engine at a 5% grade only can go up to 65 miles per hour. You might, actually, a question you might ask is, why didn't we use the 5 degrees angle? Because we already knew his force. If we knew his flat, we could actually figure out he could do more, obviously, in a flat. And if we knew that, we could do 5 degrees, then we could do vectors. We're not going to do that here. Okay? One last example. Let's say I have a small motor who runs a lift that raises a load of bricks weighing 836 newtons. All right, so we got some bricks. We got a lift, and we're going to lift it up, right? So some kind of a motor is attached, cranking it up, something like that. And it, they have a weight, so the weight, this is weight, of gravity, is 836 newtons, according to the paper, right? And they're going to lift it up 10.7 meters. Got it? What's the minimum power? Oh, over function of 23.2 seconds. A long time, by the way, I think. And how much power motor do I need to do this? So I've got the distance, I've got time. All right, so and I need to figure out the power of the motor, right? Power, all right, what's power again? Since we've got time, I'm not going to use FV, I'm going to use W over T. So if power is work divided by time, okay, or yeah, then I have, and work is force times distance over time. I know the force I need to pick up, which is 836. This is pushing down, but if I don't get 836 up, game over, right? So this is going to be 836 newtons times the distance, which was 10.7 meters, divided by 23.2 seconds, and that equals 386 watts. So you need an engine that can produce 386 watts, about a half a horsepower, right? 746, that's about half a horsepower engine, or you're not lifting your bricks. Houston, we don't have problems. Power's easy. Some new equations, but they're not hard. Sometimes they can be vectorial. Again, not so hard. Because Houston, we don't have a problem, because you guys are awesome. We'll see you in class.